Well, hi there, friends. It is another great day to learn more about calculus today. You worked on area and the accumulation of area to produce either net or total area, depending on the situation. And we're going to talk about accumulator functions today, how they can represent more than just area, but can represent something in a real-world context. So that's what we're going to talk about today. It has a lot to do with paying attention to units. So we already know that units can go down, what we call down a level, by using the idea of a derivative. So conversely, we can move up units using the idea of an antiderivative or an integral. And so if you're paying attention to how you go quote unquote up and down versus between units, pay attention to the calculus that makes that happen. So the integral is something that we use naturally to calculate net and total change, so net change and total accumulation of more than just distance, more than just area. We could use growth, we can use decay, we can use the consumption of materials, anything where you have a unit, gallons per hour, bananas per second, anything you're accumulating over a period of time, we can use an integral to find the cumulative effect of that. So this idea of accumulation, you set up an integral over an interval of time. So let's look at this. Water, this is our example, is pumped into a tank at a rate of a cubic function, t cubed minus t plus 2 gallons per hour. So that's our unit for the course of 3 hours. Find the accumulated total in the amount of water. All right, so our accumulated total in the units of gallons per hour would be an integral over the time of the 3 hours of the cubic function. And this is a total, but it's always positive. This function was always above the x-axis, so I don't have to worry about the absolute value in this case. And then dt, because we're measuring it over time. And then you can grab your calculator, do a nice math 9, and then you'd have to make sure you have the right units on your answer. So we end up with 21.75, and then the units on that would be the accumulated gallons over that time interval. So in that 3-hour time period, this tank accumulated 21.75 gallons. Doesn't have to be just water. We can talk about food consumption. We're consuming potatoes here in the millions of bushels. So this is an exponential function, 2.2 plus 1.1 to the t million bushels per year is our unit. And t being the years we're measuring since 1970. So how many bushels were consumed. So our total consumption, going from 72 to 75, 1972, so that would be 225, because we're measuring the years since 1970. 2.2 plus 1.1 to the t, and then dt, again, because we're measuring the time interval. Again, this is a positive function, so we don't need the absolute value to guarantee the total, and we'll use a math 9 once again. And so that gives us 10.802. And the units on this are millions of bushels of potatoes. So over that course of that 3-year time span, 10.802 millions of bushels of potatoes. So that doesn't even tell us how many potatoes there are, because you need to know how many potatoes are in a bushel, and then multiply that by a million. So this is a huge number of potatoes being consumed. This also applies to velocity and distance. So if we integrate velocity, so if we throw an integral here, that will result in distance. Of course, that should make sense if we're keeping track of our units. If we integrate miles per hour, we should get distance. Now, whether or not you do net or total is going to give you something different. So displacement is what we would typically consider as net. It is the positive area versus the negative area. It's the net amount of miles or distance that's covered. Now, if you want total, then you're going to need an absolute value around the negative parts of it. Final position is a different question. The final position takes into account the initial condition, where you start, okay, the starting point, and then you add the displacement to that. So final position always takes into account displacement and the initial condition. So let's practice that. So it's a vocab issue, so make sure you're reading carefully so that you're answering what's being asked. So let's consider linear motion. So we're having velocity measured by 10 minus 2t. This is measured in meters per second. We're looking at a time unit of 0 to 9, and we are using analytic methods, which means we can't use a math 9 here. So 10 minus 2t, okay, that's going to give us a linear piece intersecting at 5, and we're going out to the number 9. Okay, so that's our visual here of what we're looking at. Use analytic methods to determine when it's moving to the right, to the left, and stopped. All right, so analytic means can't use my calculator, just want to look at the graph. To the right would be positive velocity. And so looking at our graph, my right is going to be from 0 to 5. To the left would be the rest of the interval, so from 5 to 9. And then when is it stopped? It's stopped when the velocity is 0, and that happens once, and that would be at t is 5. So the displacement for the given time interval is the addition of positive and negative area just added together. No absolute values, just the displacement. So if we need to consider this triangle, so I'm going to do this geometrically, that would be 1/2 times the base times the height. So we're looking at positive 25. And then I've got some negative area down here. Okay, this is negative 8. Okay, and so we've got for that one, (1/2), the base is 4, the height is negative 8, and so that's negative 16. And so the displacement would be the positive plus the negative. So we're looking at a displacement then of only 9, and that would be meters as my displacement, 25, negative 16. All right. So what is the particle's final position? So the final position for part C needs to be the displacement of 9 plus the initial position of where it started out, which we're given right here. Okay, we're given the initial position. This started out at position 3. It's like it was given a head start, right? It's not starting at the starting line. It's starting out at 3. So this is 9 plus 3, and so this would be at 12 for its position. The total distance traveled by the particle, we have 0 to 5 of the velocity, but we've got 5 to 9 of the absolute value then of the velocity. So that would be 25 plus the absolute value of negative 16. So the total is 41 meters. Okay, that's linear motion, and I could do all of that with geometry. Parabolic motion. So now we're dealing with a curve. So I won't be able to do with geometry anymore. I'm going to need some calculus to help me out with this. And so visually, I'm looking at now a parabola curved here out to the number 9, starting at 10, crossing somewhere different now. So determine when the particle is moving to the right, the left, and stopped. I still need to find this value here. So I'm going to set 10 minus 2t squared equal to 0. And when I solve, I get the square root of 5, plus or minus, but we're looking at the square root of 5 here. And so moving to the right would be the time interval between 0 and the square root of 5. Moving to the left would be 5 to 9. and then stopped would be at the square root of 5. Okay, finding the particle's displacement for the given time interval. So I would need positive and negative added all together. So I'd need from 0 to rad 5 of the velocity, added directly to rad 5 to 9 of the velocity. And because of the property of addition, I can just skip the rad 5 altogether and go from 0 to 9. So this will be the integral of the parabolic curve, 10 minus 2t squared. So that's 10t plus minus 2/3 t cubed plus c on the value of 0 to 9. So that would be 90 minus 729 times 2/3, that 486, plus c, and then minus 0 plus c. So we're looking at negative 396. And looking at my units, this is meters. So the displacement is a net change of negative 396 meters to the left. So what's the particle's final position? Well, that displacement of negative 396 plus its, again, initial condition, it started at 3. So negative 393 is the initial, or the final position. All right, the total distance traveled by the particle. So the definition would include that rad 5 now of the velocity, plus from rad 5 to 9 of the absolute value of that velocity. So again, we can do this a couple ways. To remove those absolute values, 10 minus 2t squared dt, I can either subtract or I can change my bounds. It's really up to you and how you like to do that. So I'm going to keep my bounds the order that they are, but I'm going to subtract my integrals. All right, so I'll have 10t minus 2/3 t cubed plus c going on bound 0 to rad 5, and then I'm going to subtract the same antiderivative going from rad 5 to 9. So 10 rad 5 minus, let's see, that turns out to be 10/3 rad 5 plus c, and plug in 0, okay, and then minus 90 minus 486 plus c, and then minus a negative, so plus 10 rad 5 minus 10/3 rad 5. All right, so adding all of these together, so let's see, that's 20 rad 5, that's minus 20/3 rad 5, and that's plus 396. So adding all that up, that'll give me the total distance. We could get a common denominator, so let's see, that's 40/3 rad 5 plus 396, and we'll measure that in meters. Okay, so moral of the story, look back what we did. We're using the integral as an accumulator function to take us from a rate, which is something measured in time, to an accumulated total, whether that's a net or a total with the absolute value. But understanding how an integral can move between units is really helpful. All right, I look forward to seeing you guys on Friday. But hope you're having a great week so far, and I'll see you then.